Okay, so hello everyone. So first I want to ask, do you have any questions about the last times? Mm. So, So, last time we kind of completed this program of computations of grand functions in RD for all the equations we want to study. So, in a sense, now we can solve, or at least formally write a solution for any equation in RD. And today I want to switch to more complicated setting of boundary and initial value problems. Mm. So these are problems where our equation is defined not in RD, but in some domain in RD. So, for example, we can study the following problem. A Laplacian of u equals to 0 to rho, maybe let us put rho, Laplacian u of x equals to rho of x. This holds for x in some domain of R2 or Rn in general. Let's put RD. And on the boundary, we have, and we also have some condition on the boundary that u of x equals to some u0 of x, where u0 is given, for x in the boundary of this domain. Or another problem. That we have some equation, we have some wave equation, and well, actually, we solved such problem already in this particular case, but now I want to study this in more general setting and also prove some theorems about existence and uniqueness of these solutions, and also tell which methods can be used. Okay, so this equation should hold, for example, for some x in the interval from a to b, and there are some boundary conditions. U of a equals to u a of u of t and a equals to ua of t, u of t b equals to some u b of t, and we have also initial conditions, u of 0x equals to u0, u t of 0x equals to u1 of u0 of x, u1 of x. For example, in this equation, we fix some boundary values. So if it is some square or rectangle, we fix some boundary values for all these four sides, and in this case we fix boundary values here and here, and we also fix a function and its derivative on one of these boundaries for t equals to 0, and the other end is open. So uh, it is more or less clear from the physical formulations of these problems that this is a problem of some vibrating string, and so it is natural to give it initial conditions and fix some behavior of the boundaries. So it's natural that we fix first the function and its first derivative on this boundary, and this is a kind of electrostatics problem, and here we ask, for example, this electrostatic potential to be 0 or to be some function on the boundary, and we also put some charges inside. So it also looks natural, but from a mathematical point of view, these problems are very similar. They differ just by the sign in the equation. And it turns out that the set of possible boundary or initial value problems depends on the equation, and it's not only a physical motivation that tells us that we should consider such kind of problem. It's also dictated by mathematics, because if you try to consider this problem, sometimes it will not have a solution. Sometimes no, actually it will happen at the same time that it will not have solution for some initial values, but if it has a solution for this initial value, then the solution will be non-unique. So that we will discuss a little bit later. So the only message is that it is important to consider correct boundary or initial value problems for a given equation. So. The main methods to solve such problems will be the following. So method one is to use our knowledge about green functions in a d-dimensional space. It's for some simple problems, like in the half space or in some quadrant where we have. Oh, but actually, if we know how to compute infinite sums, it can work also in more complicated settings. So another method, this method works for arbitrary boundary conditions. Another method is to use a normal mode expansion, separation of variables plus normal mode expansion. Well, such methods should be used if we have some special initial boundary conditions, such that it is easier to solve this equation by some kind of trick adjusted especially for this condition, then rather than take the general green function and integrate with it. In the case when we know this green function. So sometimes it might happen that we just don't know it. Mm. So, and there is there is a normal mode expansion. So, and this third method, or group of methods, is something that works for some small dimensions, some special equations. It's something like D'Alembert like formulas. Mhm. Sorry. Or conformal maps. This is the case where we can write a solution of some equation almost explicitly, in a sense, like for the wave equation, we know that arbitrary solution is just a combination of two functions of x plus t and x minus t, and when we know this, we can do anything. We just need to find this function. Or if it is not the wave equation, but 2D Laplace equation, we know that its solution is a holomorphic plus anti-holomorphic function, and we can use all the techniques that can give these functions. And then, if we are in the situation where some of these methods are applicable, we can try to recover the same results in a different way. But it might happen that there is some shorter path to get such solution. Okay, so are there any questions about this? Classified answer uh, is essential. Okay, so let us maybe proceed with this. So maybe um, so what? Let us maybe first talk about existence and uniqueness, and then consider some particular cases. Mm. Mm. Uh, So, namely, let us first discuss difference between wave and Laplace equation. So, first, let us consider a wave equation. So uh, uh, we want to, so as I said, in this case, we need to choose boundary conditions of this kind, that we fix uh, u and ut, u of 0x, ut of 0x on one boundary, and some boundary values, for example, u of u of t x for x equals some u boundary of x for for t and x when x is in the boundary of some domain d. So let us first discuss uniqueness. Because, for example, we know that a solution of this equation exists because, for example, we know it's a green function. So at least if it is something in the whole space, we can write some explicit solution. But we still have the question of uniqueness because, for example, when we computed the green function, we had a lot of freedom to add some solutions of the free equation without right hand side. So this should be studied. And since we have linear equation, then this question always reduces to the following question. So suppose that we have some solutions u1 t minus u2 minus u1 minus Laplacian of u1 equals to some function. And we have another solution, utt2 minus Laplacian of u1 or minus Laplacian of u2 equals to f. u1 and u2 are two solutions. So if you now take the difference u1, let us call it u12, equals u1 minus u2, then so it's a linear equation. We just subtract the two and get that it solves a equation with zero right hand side. And so Laplacian of u equal to zero, and boundary conditions are also zero. So this difference solves the equation with zero right hand side and with zero boundary condition, zero boundary and initial conditions. So all these conditions are zero. And to prove uniqueness, you we need to show that this solution should be identically zero. So it can be done in the following way. So let us study the energy corresponding to this equation. The energy functional. So this energy that depends on u of t and x in the integral from integral between the boundaries from oh, integral over d d dx gradient of u squared. And we would like to find its time dependence. Or to be precise, time independence. So we want to compute d in dt of this energy. Mm. So so we just maybe it's better to put here 1/2 because usually energy is defined in this way. So we differentiate this expression under the integral and use sorry, I forgot the most essential part, dt u squared. So is it better to write it on the next one, on the new line? Maybe yes. So on the new blackboard, let's go to the new blackboard. So, and by the way, we work in the d plus one dimensional space. In a sense, it is integral only over the space variables. So t x is a point of r 1 plus d. So it's the integral over some slice at time t. Okay, so we differentiate it in t, and it is what? It is the integral gradient of ut, gradient of u, plus d t t, or maybe let us write u t t times ut. And now we can use the wave equation here. So it's integral dx gradient of u t gradient of u plus Laplacian of u times ut. So now we want to bring this two terms to the same form, and to do this we need to integrate this by parts. So it's integral over d. So we'll have the integral over d. So it is this integral by parts. If it is just a single, if it is a 1 + 1 dimensional problem, it will consist just of two terms on the two boundaries. So the boundary will be 0-dimensional. Plus integral over d dx ut minus ut plus n of u plus ut plus n of u. And now, so there is some tricky point. If we consider the problem with mixed boundary conditions, where we have some relation between u and its x derivative. In this case, so physically it corresponds to some string attached to the end of string, and physically it means that we should also include the energy of the string. So we need to add some boundary term. But if we have u equals to 0 on on this boundary, or we have gradient of u, so n gradient of u gradient of u equals to 0. If you have this, then this term vanishes. That normal derivative of u at the boundary is 0. So so there is a boundary, and there is some normal vector to this boundary. So is it okay? So one of these terms, either ut or this gradient of u vanish, and so this boundary term is 0. So, but if you write mixed conditions where there is some linear combination between u and this gradient of u, then we need to add some quadratic term in u, which is the energy of this spring that gives this boundary condition. But maybe it's better not to go into the details. So, easier to study such usual boundary conditions. And this is 0 just because they are identical terms. So we see that and this energy is 0, right? So so if we take two, so if we take some function and that was 0 initially because of this initial conditions, then this so how to say it, so if this energy of u of u1, 2, maybe not if, but just little statement. So this energy of maybe I should also put here some sign t, which means that this energy is computed for some time t. So this energy of u 1, 2 of t and x equals 0, just because both u and its time derivative are 0. So it is constant with time. Time derivative of the energy is 0. So energy at arbitrary time is also 0. But we know that this energy is a sum of squares of two derivatives. And therefore, this function u12, which is the difference of the two, is constant. And since we know this constant at t equals to 0, it equals to 0. So we already proved that solution of the wave equation is unique. So is it fine? Hmm? Yeah, so of course you can. But if you want to call it Hamiltonian, you should call this momentum and define Poisson bracket between momentum uh, and u. So this Hamiltonian will be the integral of 1/2 of gradient u squared plus p squared and a Poisson bracket between p and u should be so p of x, u of y should be. Hmm? Yes. So, this when you switch to Hamiltonian description, we have one distinguished coordinate time, and we introduce some momentum that will replace this time derivative. But this is some infinite dimensional mechanical system, so degrees of freedom are now labeled by coordinate. So we need to write this Poisson bracket between p and u in this way, this delta function. Or we can first switch to mode expansion and then write this Hamiltonian formulas for each mode. It will be the same. So, hmm? Hmm? No. What do you mean? So we have two options, two different boundary conditions for this to work in this simple form. One option is to say that you use zero on the boundary, then its time derivative is also zero, and that's all, right? Because it is constant with time. Because as a function of t, it is zero. It is zero for any moment of time. If you differentiate in t, it's boundary value, it's not initial value. Mhm. So, and if in this if gradient is zero, then we don't even have this question. It is just zero, so we don't need to differentiate it first. Mhm. Uh, Okay, so we know that solution of this problem is unique, but let us ask what breaks if we try to take these boundary conditions from a different equation. Mm. Uh, so. mm, so namely, let us study this u gt minus u x equals to 0 with boundary conditions q of 0. Uh, let me just draw some rectangle or circle. No, better take a rectangle. There's x, there's t, and here 0 with 0, 0. Here is L, here is some T. So so it is our domain, and we ask U on this boundary equal to some U0. Uh, so the first problem which we meet is on the following. We know that U the generic solution of this equation is given by some f of x plus t plus g of x minus t. Mm. And let us now study some rhombus of this form, maybe rhombus or mm, yeah. So let us study something like this. Uh, so this coordinate is mm, some, it would be some tx. here it will be tx plus plus a minus a. Here it will be tx plus 0. No, no, sorry, it is minus a. So here it will be so, and here it will be so uh, let us call this point 1, 2, 3, and 4. And let us write the value of solution of this wave equation at this 4 points. So u1 equals to just some f of x plus t plus g of x minus t. u2 equals to what? We change the sum of t and x, but we don't change the difference. So u2 equals to f of x plus t minus 2a plus g of x minus t. u3 is f of so here it works in the opposite direction. We don't change g because their sum is the same, but we change f. Oh no, so we don't change f. Yes, their sum is the same, but we change g. So it will be fx plus t plus g of x minus t plus 2a. And for u4, we change both of them. No, sorry, here probably I made some mistake. Because here we change t, not x. So minus 2a x. Coordinates are this: x, t, and x. So here, this one is x plus t minus 3. Yes, thank you. Yes. So now let us try to take the following combination of these functions. So we want to get some linear dependence of this for use. Let us try to construct this. So we definitely need to cancel these terms. So it should be u1 plus u1 minus u3. Well, these terms should be cancelled, and also this So the other expression should be u2 minus u4 to cancel these terms with some coefficient. So let me write it later. u2 minus u4. And so if you consider this, then this will be cancelled. But let us actually compute what it equals to. Uh, Let us put some coefficient here. So this expression will be g of x minus t minus g of x minus t plus 2a plus some coefficient times u2 minus u4 is g of x minus t plus minus g of x minus t plus 2a. So we see they are the same. So c equals minus 1, and this equals to 0. So we know that u1 minus u2 minus u3 plus u4 equals to 0. Right? So which means that if we have some square domain, so if t equals to L, we have this relation. So it means that we cannot choose arbitrary boundary conditions. Actually, so I considered here the simplest case because otherwise, so even this was a little bit complicated to write on the blackboard. But actually, there are more conditions. So if I remember correctly, there are also this. So this should be 0, and there are also conditions of this kind. It should also be 0. So there is some infinite collection of such conditions. Okay. So the first problem which we have is that not so boundary conditions are not arbitrary. But it's not the only problem. It is as usual in the linear algebra. If you have some system that should have unique solution from dimensional reasons, but it does not have this solution for some subset of the right hand side. It means that it should also have different. It should also have some problems with the uniqueness. In a sense, if we have kernel, we should also have a co-kernel. And let us see how this works in this case. So when t equals 12, we can write solutions of this wave equation with zero boundary conditions. And this, so non. So we have solutions of the form Mm. So, is it clear that first it is a solution of this wave equation, and second it is a zero on the boundary? So, that's product of two functions. So, I don't know. No, maybe we can draw some picture for the solution. Uh, so it looks like this. We have some. We have some. We have zero t equals to zero. T equals to zero. And then we have this. So this is u. T, ux. Mm, oh, it's from zero to u. It's t. It's zero. So for t equals to zero, we have zero. Then we have some, for example, a sine wave at some different time, and then at time t, we have again zero. So problems with such properties are called non-well-posed. Non-well-posed. Uh, So well-posed problems are those that have solution for arbitrary initial conditions and depend continuously on these initial conditions. Non-well-posed problems are those that don't have a solution for generic boundary conditions. So this is uh, uh, maybe the simplest example of such problem. So so we see that here this problem appeared because we had some special geometry for this boundary. In principle, we can choose T and L such that their ratio will be, for example, square root of 2. And namely, we will not have this this restriction on the boundary conditions. But you see that it is some condition which is super sensitive to the shape of the boundary, and it is also sensitive to initial conditions, because we will have some small denominators in this problem. So. Uh, so even if you have some arbitrary shape of the boundary, it will still be not well-posed problem. Mm, mm, so are there any questions about this? And yes. No, no. Uh, 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 so What is the analogy of that? Hmm? No, but it's not a problem. It's a feature in that case. Uh, uh, so do you mean a square in a coordinate space? Hmm. Uh, but it's not a problem, it's a feature. In a sense, you have many states with the same energy. You can organize some symmetry group acting on them. So it is good. Uh, No, because here the problem is that such functions are acute by this equation, by this differential operator, because there is minus sign. In quantum mechanics, they will just have the same energies, which is nothing bad. So. Oh, it can cause some problems if you consider some perturbation theory, where we have differences of different energies. But it's again not a problem, but a feature of this problem. Mm, so extra symmetry never causes some real problems. So. Mm. Oh, for example, in this case, Laplace equation on a square will not be different from Laplace equation on a rectangle from the computational point of view. Okay. And by the way, so far we studied a uniqueness of this solution, and if you want to prove existence, it is well, maybe I can fit here. Uh, so existence. So we just write that u of t and x equals to sum of uh, uh, so we write that initial values have some Fourier expansion. We actually did it at some moment probably, but we can just repeat it in a little bit different context. So u0 of x can be expanded as some a n sine of pi n x over L. Uh, u1 of x is mm, sum of bn sine of pi n x. Oh, sorry, over L. Pi n x over L. And mm, uh, a solution of this equation is mm, so it will be some a sum of a n cosine of pi n t over L sine of pi n x over L plus sum of bn sine of p pi n t over L times Actually, I should have put it here. Simplicity. Oh, uh, so please look at the solution. So is it clear that it actually solves the wave equation utt minus uxx equals to 0? Hmm. Hmm? No, because the first thing to do is to find basis of functions that diagonalize dx operator and satisfy boundary conditions. So first of all, its existence for the normal problem. Because we know that this problem with some boundary values is ill-posed, and we should not hope to find its solution. We prove uniqueness in the same setting as we prove the existence. We prove existence in the same setting as we prove uniqueness. So, so it's for the normal problem. But who is T? But wait, we have already found that such problem with boundary conditions is ill-posed. Um, so, so no, once again, we proved uniqueness in this setting, where we fix initial conditions u0 of x equals to this, and u1 of x. So and this is some u1 of x. So we fix a function and its variable at time equal to 0. And so we know that this problem is good. We know that its solution is unique if it exists. And now we want to prove that it exists. And we do it by explicit construction. Let me change the maybe like this. So, so is it clear that this function solves this wave equation? Yeah. Because both derivatives act by the same number on this and the function on this. And then it should also be clear that it solves these conditions that u of 0 and x equals to 0 of x, and ut of 0 and x equals u1 of x. Because when we differentiate, when we just put t equals to 0, all the terms vanish. And only surviving terms are this. So cosines turn into 1, and we recover precisely this expansion of u0. And if you compute time derivative, this term, time derivative is 0. These terms vanish because time derivative of cosine is 0. And these terms, derivative of this term equal to 1. So so we recover this other Fourier expansion. And so the only problem with the existence of this solution could be that this series is divergent. But we know, we see that these coefficients have absolute value less than 1. Some these coefficients, and it was no. So what do I want to say? So these prefactors have absolute value less than 1, and it was the same here. So so if this Fourier series were originally convergent, then this Fourier series is convergent as well. So so you maybe I can write it here. U0 and U1 convergent. So U is also convergent. And I'm emphasizing it here because it is another point in the proof that can in principle break. Because here we see that this mapping between coefficients in the initial conditions and coefficients of expansion of solution. So this method contains some functions with absolute value less or equal than 1. But in principle, there can be some exponentially growing functions, and it will actually happen with this Laplace equation. And also for the heat equation. And by the way, here you saw this application of this method to solve this wave equation. So, for example, if you had just some finite number of terms in this u1 and u0, we could just take this formula and write explicit formula for a solution. So, sum is from 1 to infinity. And here as well. And oh, and if I try to write some green function for this problem on the interval, it will be probably more complicated to get the solution using the green function. So, are there any questions about this? So let us now go to the next problem, namely to this Laplace equation. So Laplace or Poisson equation. So I will raise. Yeah.
So we have seen that there are some
Mhm. But what do you mean? So, yeah. By that you mean the type of initial conditions? But I don't think that we have um, many options here. So maybe we can generalize this initial conditions if we work in some relativistic setting. In a sense, we can fix this initial u and ut on some surfaces that lie outside the light cone. So we can in a sense, some problems with this boundary appear when it is rotated more than by 45 degrees when we cross this line x equals to t. So in principle, we can choose some initial value surfaces in some other way, but everything else is the same. In a sense, we can only give u and ut on some surface and fix u or ux on some other surface of this kind. Yes, yes. Mm. Of what? In, oh, but if you take some linear combination instead of u and ut, we will have just not enough conditions. You need two conditions because it is second order. This equation is second order NT. So we can get linear. We can take linear combinations at the boundary because we have one boundary condition on each side. So. Okay, so any other questions? So let's go to this Poisson equation. So so the simplest way to think about this, if you want to repeat this arguments, so the simplest way is to say that this so we need to find a solution for the equation of Poisson of u equals to 0 with boundary conditions. Or let us say, for simplicity, that u and d equals to 0. Uh, so So we can say that these equations are equivalent to condition of minimality for the following energy functional. So it's a little bit different energy functional, or uh, in a sense that any variations of this, so I didn't write who is this functional. So it's on the same but without time derivative. Uh, so if so if you compute its variation, we need to substitute. We need to compute this energy function of u plus delta u, and this equals to integral in dx over d u gradient of 1/2 gradient of u squared plus 1/2 gradient of delta u squared plus maybe let me put here some small number epsilon plus epsilon epsilon squared plus epsilon gradient of u gradient of plus gradient of delta u. And now we can integrate one of these terms by parts and get e of u, this term, plus epsilon squared e of delta u, plus integral over this domain minus integral over this domain delta u plus n of u plus plus the integral over the boundary. So delta u dn delta u gradient of u. No. Delta u is just some arbitrary function, and this no, we want to take a variation of u with arbitrary function. So by definition, I didn't write the definition. So definition of this rational derivative or rational differential delta E of u is by definition d in the epsilon of E of u plus epsilon delta u for epsilon equals to 0. So it depends on no, it is a function that depends on delta u. It's like full differential of a function, like d df of x1 and so on xn equals to sum of df over dxk dx dxk from k equals to 1 to n. So there is this formula for the full differential of this function, and in this rational calculus, the analog of this formula is this. Delta E of u equals to the integral in dx ddx delta E of u in delta u of x delta u of x. So this is a kind of single character, which means df, which is analog of df over dx k. And this is just this function delta u. So if you look at this formula, if you take the term at the first, okay, as epsilon, if you take this term at the first order of epsilon, it will have this form. It is the integral of delta u of x times some function and this function is precisely our equation that we want to solve. So, so we can say that this delta E of over delta U of x equals to minus Laplacian of U of x. So, is it clear or not? So here. So it is just some analogy. So mm, the general setting in this rational calculus is the following: we have some functionals that depend on functions on some manifold, for example, and the analogy between functional and function is the following: a function depends on some of finite set of variables, and so it is its argument. It is some set of x1 and so on xn, and argument of functional is a function. And to describe a function, we need to give all its values at all points. So in some sense, values of this function u at all points are the arguments of this functional. So then, if we try to take a full differential of this functional, we should have some analog of this formula. That a full differential of a function is sum over all variables, d for this variable times differential of a variable, and so. This summation in n will be replaced by the integral over the whole space, and we see that actually, if we try to compute this functional at a little bit shifted function, the linear term is proportional to delta u, in the sense that it is some integral delta u of x times Laplacian u of x. So it has precisely this form. It is the integral over the whole space of delta u of x times something. So, and the definition of this rational derivative by u at point x is precisely this. It is the coefficient that stands in front of delta u of x. So, but it is a kind of notation. We don't even need it to formulate the statement, because the statement is the following: a condition that a condition that this functional should be minimal is equivalent to the Laplace equation. And we are checking precisely this. So suppose it is minimal. If it is minimal, it means that any change of a function should increase its value. So the first order change should be zero, because if it is a minimum, then it should be a minimum in all possible directions. And we choose the direction by choosing some delta u, multiplying by epsilon. Well, the first order term in epsilon should be zero, and the second order term in epsilon should be positive. So.
Equality holds if we are with we get to the hypothesis that the Laplace equation holds, right? Not in general.
No, the definition of delta u in delta e in delta u, and a condition that Laplace equation holds means clearly that this delta e should be zero.
This function e for physically represents some sort of energy.
Yes. For example, it can be the energy of electric field if it is an electrostatic problem, or if it is a problem about membrane, it is the energy of membrane. So, actually, this Laplace equation can be considered as a stationary problem for some oscillating membrane, and some that a time derivative disappears, or a stationary problem for the heat equation. But for the heat equation, probably I don't know what is the interpretation of this energy. Oh, something strange. Yes, so So, hmm? Hmm?
The general case, the variation, if I have the classification without Laplacian equal to 0, then the variation is equal to rho.
No, in that case, we need to insert this external source into the functional. So probably I can erase this. So in this case, delta E will be this minus delta U Laplacian U plus rho plus delta U times rho ddx. So so it is the energy of interaction between this electric field and external charges. But so why I wrote all this? Because we know that we have the statement that Laplace equation is equivalent to this minimality of the energy functional. And now suppose that we have mm, uh, suppose that uh, uh, Laplacian of u is equal to 0, u on dd is equal to 0, but energy of u is not 0. Uh, and since this energy is mm, is positive, it means that this E of u is greater than 0. But and it is not minimal because we can simply take so E of this u is greater than E of just 0, which is 0. So minimality in this case implies that E of u is 0. But if it is 0, it means that gradient of u is also 0 in all points. So it means that u equals to a constant. And then it depends. In principle, we could consider such boundary conditions with a fixed derivative of u. It is allowed by this term. In a sense, normal derivative of u can be zero. It it allows us to have non-uniqueness up to some constant, because equation itself contains derivatives. Boundary condition contain derivatives. So in this case, it is allowed. But if our boundary conditions are u equals to zero, it means that this constant should also equal to zero, and the solution is unique. So, any questions?
Compute the limit for epsilon that goes to zero of the difference between e of u plus epsilon times u minus e of u, and then we get the first term, okay, is equal and divided by epsilon.
Yes, but we see that it is just constant term which cancels. There is a term proportional to epsilon, and there is epsilon squared. So we just need to take this term at epsilon.
And the last one, why vanishes?
Because either delta u equals to zero, or this or this gradient equals to zero, because we should consider variations only in the class of functions that satisfy boundary conditions.
Okay. Okay. If we choose a function that satisfy the boundary condition, okay, and why the gradient?
Yes, because we can in principle consider boundary conditions when gradient of u is zero, or when u is zero. So there are two options. And both of them work. In a sense, this last term vanishes in both cases. Actually, I think also in this case, there are this mixed boundary conditions that involve some linear combination of u and a gradient of u. But in this case, there will be the same problem. In some, this term will not vanish, but probably it will equal to something computable, and it should be then included into the energy. It will mean some kind of mechanical system living on the boundary. I don't know, so some charges connected by springs or something like this. So we will need to change the energy function for this system. And probably it's too complicated. So, okay, so are there any questions about this? Actually, so there is another proof of uniqueness of the solution, which works for Laplace equation. Namely, people prove that if some function solves a Laplace equation, then it means that its average value over some sphere equals to the value at the center of the sphere. For example, it is either checked for two dimensions. dimensions. And then, so it's called, so it means that the maximum of this function can be achieved only at the boundary. It is called maximum principle, but and probably it can be a little bit easier than this energy functional. But advantage of this method is that it can be easily extended to the case of a Helmholtz equation. Namely, we just need to add another term, which is n squared u squared to this energy functional, and everything works absolutely the same. So, there is this small advantage. Uh, and now let us ask the same question. We proved that this problem with boundary conditions is nice. Actually, we need to check that a solution exists, and probably we'll do this next time. And now let us ask a different question. So, what happens if we try to do if we try to solve a different problem? What if we try to solve initial value problem in this case? And now I want to use an advantage of having the blackboard and just take these formulas. So maybe it's the question to you. What happens if we change the sign in this equation? How can we modify this formula so that it gives a solution of the same problem with the same initial conditions and same boundary conditions, but of different equation? No, no, there is small modification. So, hmm?
Maybe T dependence
Mhm.
should not be on, I don't know, because like I was trying to do separation of variables,
Mhm.
and it turns out that maybe the T dependence should not be with cosine,
Mhm.
but the exponentials.
But there is a nice basis in the exponentials, which is basically a hyperbolic. Yes, and that solves that solve the same equation but with opposite sign. So yeah, so you can write a cosh of this and a sinh of this.
So maybe we could figure out by doing this substitution T equals I tau,
Yes.
and then okay.
Hmm?